Hi everyone, and welcome back to Power Electronics Lectures. Today we'll continue talking about the buck converter, the step-down DC to DC converter. Last time we talked about how to derive the relation between the output voltage and the input voltage for this converter, and we found that the relation between the output voltage and the input voltage is equal to the duty cycle that is sent to this active switch. Today we'll know what are the constraints or what are the limitations that makes our converter works in a continuous conduction mode, which means we agreed that these two switches try to store energy inside this inductor, and this inductor in such way transfer the current to the output. If all the energy stored in this inductor is transferred to the capacitor and the load before the duty cycle turned off, or before the switching duty cycle became zero, the operation is termed to be discontinuous conduction mode, since the inductor current has reached to zero. If the duty cycle is turned on before the current in the inductor reaches zero, the continuous current flows in the inductor, and this operation is considered as a continuous conduction mode for this converter. Let's revise first the operations for this buck converter. We said here is the active switch and here is the passive switch, the diode. And we said when this active switch is on, then this will be conducting, and the current will flow in this direction. The current will flow in the circuit in this direction, and the diode of course will be off. And if the transistor is off, then the switch will be off and the diode will be on, and the current will be flowing in this direction. And also we said that if you look at the current on this inductor, you will find that the current when the switch is on will have a positive slope, and when the switch is off, the current on the inductor will have negative slope. This is the current on the inductor, and this is the switch. We said that here is the duty cycle times the switching time, and here is the switching time. We also agreed that to achieve a steady-state operation, the average current in the capacitor and the average voltage in the inductor must maintain zero. We said that the average voltage that is applied on this inductor must be how much? Must be zero. The average must be zero, so this area must be equal to this area. When the inductor is charged, we have positive voltage. When the inductor is discharged, then we have negative voltage. These two areas must be exactly same value. Otherwise, the charge, the current, the energy will be accumulated inside the inductor, and then gradually the inductor current will be increasing until we reach unstable operation, or the device might be damaged. The same thing happens inside the capacitor. Within the capacitor, we know that the capacitor absorbs the ripple. So the average current across the capacitor must be equal to zero. If we try to draw the current on the capacitor, you will find that the current will be something like this. Here we have two areas. This is the current inside the capacitor, which equals to the ripple that is taken from the inductor. And in order to make sure that we have a stable operation, so this charge here, this charge must be exactly equal to this charge. If these two charge or these two areas are same, so definitely we have a stable operation or balanced operation, and our converter will work properly. So we have like sustained output voltage. Otherwise, let's say the charge, the positive charge is larger than the negative charge. So again, the charge will be accumulated on the capacitor, then the capacitor might be damaged, or we might have an unstable operation. So this is the case for the voltage and the current inside the capacitors and inductors. For the inductor, the average voltage will be zero, and for the capacitor, the average current will be 0 or the average charge will be 0 to achieve balanced operation. So again, to achieve a steady state operation, the average current in the capacitor and the average voltage in the inductor must maintain 0. Otherwise, the capacitor voltage will keep increasing and the inductor current will keep increasing until the waveform loses the control and the capacitor or the inductor will be damaged. Accordingly, the average current on the resistor will be the same as the average current in the inductor. So when the average current on the load or on the resistor is equal to the average current on the inductor, IR will be equal to IL, because the ripple will be absorbed within the capacitor. This will be V out over R, right? What is the average current in this inductor? It will be how much? If this is the difference, delta I, the value from here to here will be how much? Delta IL over 2, and from here to here it will be delta IL over 2. So the maximum current on the inductor will be how much? The average current on the inductor, which is the same as the average current on the resistor or on the load, plus this small ripple, which is delta IL over R, delta IL over 2. Last time we found that delta IL, the change of the current from here to here, from the slopes, is equal to how much? V out over L times 1 minus delta times Ts, right? Because we said L di by dt is the voltage across the voltage across the inductor, and this voltage is equal to how much? If we say this slope is equal to how much? V out, V input minus V output over L, and the slope here again is minus V out over L. The duration from here to here is how much? 1 minus delta times Ts. So delta L is equal to how much? Delta I is equal to how much? This value times the time period here. So we can easily say that L di by dt is equal to V out over L, and di by dt is V out over L, and di is equal to how much? V out over L times 1 minus delta times Ts. So this is delta I. Delta I over 2, we can simply divide it by 2, so this will be how much? IL, which is V out over R, plus delta IL over 2, which is 1 over 2 times V out over L, 1 minus delta times Ts. So this is the maximum current. This is the maximum current, the peak value here for the inductor current. So IL maximum is how much? V out times 1 over R plus 1 minus delta. Ts can be switching frequency on the denominator. So this is 2 times L times the switching frequency. So this is the maximum current that is applied on the inductor. Similarly, we can find the minimum current here, the minimum peak for this current, for this ripple, which is exactly how much? This value minus. So this is the minimum current. So the minimum current in V out times 1 over R minus 1 minus delta over 2L times switching frequency, and the maximum is V out 1 over R plus 1 minus delta over 2L times the switching frequency. And again here, just to make it clear, the IL minimum is equal to how much? IL minus delta IL over 2. By this way, we found the limits for the current, the upper limit and the lower limit. Let's try to use these values in order to find how much is the minimum value for the inductor that keeps the converter working in the continuous conduction mode. So we agreed that IL minimum is equal to how much? V out times 1 over R minus 1 minus delta over 2L times the switching frequency, right? In order to keep the inductor current above 0, so this is the inductor current, we said this is a balanced operation. In order to keep this current above 0, so this minimum value here must be larger than 0, right? So IL minimum must be at least 0, or above than 0, larger than 0. So let's take this IL minimum, which is V out times 1 over R minus 1 minus delta over 2 times L times the switching frequency, and make it 0. So at this is the borderline between the continuous and the discontinuous conduction mode. Try to solve this. You'll find that here we have V out over R equals to 1 minus delta over 2 times L times the switching frequency. Make some simplification here, distribute the values. You'll find that, well, here is V out. We can remove V out from the beginning. So here you will get that L times the switching frequency is equal to 1 minus delta times the resistor value, the load value, over 2. And this combination is the minimum for us to keep our conductor in the continuous conduction mode. So here you can find that when we increase the switching frequency, we have some room to decrease the inductor value, okay, because the operation will be faster. When we decrease the switching frequency, the inductor must be larger in order to keep the operation in the continuous conduction mode. So here, the inductor times the switching frequency, the minimum value for this must be how much? 1 minus delta times R over 2. And this is the minimum values for the inductor and the switching frequency to keep the buck converter in the continuous conduction mode, or at least in the margins between the continuous conduction mode and the discontinuous conduction mode. I'll stop here for today, for today's lecture. Next time we'll continue talking about many interesting things in buck converter. We'll spend quite good time in buck converter, not because it's a buck converter, but because it can be considered as the basics for the DC to DC converter. Next time we'll talk about the design of buck converter, how to design buck converter, how to select the values of the inductors and the capacitors, for examples, what are the ripple range for the capacitor, and many interesting things yet to come. So keep with me and see you next time.